Ta-da.
Good.
Renee, can you maybe start sharing a link to the paper in the chat so that people can see it?
Hello.
Hey, hey.
Hello. Okay.
We are streaming.
We are streaming. You have the link. I'm gonna make me make someone else co-host just in case. And I make you host.
Yay.
And then you hit record and I leave and we hope it works.
It was the record now.
For everyone online, if you get kicked out, there will be a recording later.
Okay. Cloud
Ready?
or PC? Do we have a cloud?
Yeah, it's gonna go into the Zoom account.
Okay.
Here we
I
go.
think we are recording.
Good luck.
Lilith is joining. Thank you. Okay, welcome to this almost last Neuroccino for this year. After a good deal of technical issues, we're finally streaming. Um, so today we have Irene presenting for the first time, and we have a paper on the topological trajectory, structure and trajectories of the human brain, as far as I know. So take it from there, and the floor is yours.
Thanks. Yeah, so the paper I want to present is this huge and extensive paper that has been recently published in Nature Communications. And the whole idea of this was that the authors wanted to map the structural relationship changes across the whole lifespan. And so let's say that started with a bit of background. So we know that both from the functional and the structural point of view, the brain relationship between areas and structures is changing with the development and but also with the more aging stages. And overall, what we know is that aging is associated with reduced connectivity because of the pruning of weak connections, and that it increases modularity and more rich club organization. So overall, this paper will focus again on, as I was saying, on structural data. And they wanted to explore through graph theory matrices. But also what they wanted to do is to visually see the changes across those measures. So what they will do is again graphically represent those relationships and to identify what they call turning points, so points of change in the direction of the changes basically. So shifts in into the trajectory of those topological measures. And so specifically what they did was to first characterize the connectivity development. So here we're talking about connectivity, but it's always referred to structural connectivity to explore three different types of measures, topological measures, so integration, segregation, and centrality. And then they applied UMaps to define what are the manifold spaces and to identify those major turning points. And then, of course, what I wanted to do is to understand why those are the critical turning points across the topological development. So I will quickly go to the methods just to give you a couple of information. So this is a Nature paper, so the methods are in the end. So they selected 9 different data sets, and with those, they were able to cover the whole lifespan from 0 to 90 years old. So the datasets were all publicly shared datasets, including the calm dataset, red dataset ACE for the younger group, then the developing human connectome project and the human connectome project development. Then they also include the human connectome project young adults and the aging. And for the last part of the aging trajectory, they also included the Cambridge Center for Aging Neuroscience dataset. So overall, what they did is to calculate trajectory measures in a deterministic way. And of course, they had to harmonize across those datasets because those were they were acquired with different acquisitions. And then what they did, because they applied graph theory, they thresholded the connectivities. And they did that by selecting the top 10% connections, which is like the usual practice, more or less, in graph theory. Usually you go with different thresholds and you look at the consistency in the results, but here they just wanted to select the 10%. And then they applied, they used the UMAP framework to visually represent the relationship between topological measures and to calculate the modifications. They applied the Euclidean distance. And then what they did is to reduce the dimensionality of the data, because of course we can imagine they had a lot of data to identify the turning points, and so they applied then two different they identified those epochs as the age range, and they applied the lasso of regression and a principal component analysis to understand the relationship between age and topological measures. So starting with, okay, so overall they had a data set, a sample of 4,000 individuals, which is quite large. They first started with identify the differences at the connectivity level, so general connectivity. And what they observed is that the percentage of connections changed in a nonlinear way across the lifespan. But when they focus on the node strength, which is the sum of the connections between, in this case, voxels, in this case, they found instead a linear pattern. And so here is just something like a summary of what they actually did. And overall, here is the age span for each data set and the change in density between males and females. And this is what they did, basically. For what concerns, as I was saying before, so they focused on three different measures: integration, segregation, and centrality. So integration means how easy it is for the network to communicate across these regions or structures. The segregation instead is the network capacity to be specialized for a specific process. And instead, the centrality is related to identify which are the structures that are most central in the network, and so that they facilitate the network communication. Overall, what they saw is that those four are the measures of integration. So overall, for the global efficiency, they saw that there was a decrease in global efficiency around 10 years of age, with then a little more increase until 30 years old, and then after 30 years old there was this decline until the age of 90. For the other three measures of integration, actually, they observed the opposite pattern. So basically, again, with this change in direction curve at the beginning, but as opposite direction, and then with a slightly increase with aging. For measures instead of segregation, this was a little bit more complex, but overall, the segregation seems to increase with aging. And when it comes with the centrality, again, there's a little bit of increase with a specific, let's say, down point for between the centrality around the age of 30. So they in overall what they say is that they also found some sex differences, but in this paper they didn't go more thorough on this. And overall, taking all the measures, it seems that around 30 years old is one of the peaks of changing in direction of in the directionality of the relationship between topological measures and age. So what they wanted to do is basically put together all those measures to understand which are the points of change, not specific to the measure, not specific to this distinction between integration, segregation, and centrality, but overall. And so what they identify is that the major turning points were around age 9, 32, 66, and 83. So they defined 5 different epochs, one that was from 0 to 9 years old, one that was from 9 to 32, which is pretty huge, considering also like development. And the third epoch was from 32 to 66. The fourth was from 66 to 83, and the fifth was from 83 to 90 years old. Okay, so here what they basically are displaying is the results of the two analyses, so the lasso regression and the principal component analysis. So what they did was to identify for each of these 5 epochs which were the strongest predictors of age and which were the stronger predictors that were driving the directionality changes across age. And so we can see that those are really different across the 5 epochs. So it means that the kind of relationship that there is between structures changes across the different age stages. And then for some of the epochs, actually those two predictors, so the one that was more predicting the age and the one that was more predicting the change in the directionality of the effect, were the same. So specifically going into the 5 epochs, they found that for the first epoch, there was an increase. So between 0 and 9 years old, there was an increase in small wordness. And in this case, the clustering coefficient was the crucial predictor of age. So overall, what they say is that there was decreasing integration, and that basically within this epoch, being able to characterize whether an individual was like 0 years old, 2 years old or so, was related to the extent to which the nodes are interconnected. Okay, so then around 9 years old, there seems to be a shift from like importance from the clustering coefficient to the small wordness. And specifically, what they say is that for the second epoch, so between 9 and 32 years old, there was instead increasing integration. So before we had decreasing integration, in this case, we have in epoch 2, we have increasing integration, but a decreasing global segregation with an increasing in local level segregation. So it seems that for this specific epoch, there's a huge, like more specialization of the structures, but also an increasing in the intercommunication between them. They talk a lot about this epoch, which is, I guess, nice because they call it like adolescence epoch, meaning that what they say is that the relationship between structures and brain functionality basically stays with the same trajectory between 9 years old until 32. So if we reason on the changes that can happen between an individual that is 9 years old and another one that is 32, it's nice to see that the brain functions in the same way when we are 9 years old and until we are 32. So I think that for most of us, there's still some space to let's say to boost our brain. Then the third epoch is referred to the main part of the adulthood, so between 30 and 60. And in this case, there's an increasing connectivity between regions that are close together. And there's an overall network integration decrease with some centrality changes. So meaning that the structures become maybe a little bit less fundamental in the overall network communication. And then overall, from the segregation point of view, this is the point where segregation starts to increase again. For the fourth epoch, so the early aging, they observed modular changes with a decrease in integration and an increase instead in centrality. And specifically, what they say is that from 83 years old, so the end of this epoch, what they observed is that there was more importance of the individual nodes, so like local network information compared to the global one. When it comes instead to the late aging, so from 80 to 90, more or less, they didn't find very strong significant results, and this could be linked to the fact that actually the sample size for this epoch was really reduced compared to the others. But overall, the trend that they observed is that there was an increase of centrality measures related to age, so overall, this is linked to the increase also in the segregation related to age, meaning that there's a reduction in integration, an increase of segregation. So specific structures become more central across the overall whole brain. And so after that, to basically identify general patterns of changes, they applied the principal component analysis because they wanted to look across the integration, segregation, and centrality measures. And they identify three principal components. The first one was mainly formed by segregation measures. The second one was more integration. And the third one was a combination of segregation and centrality matrices. And what they observed is that they found significant shifts in PC1 and PC2 between epochs 1 and 2 and between epochs 2 and 3, meaning that there were significant changes in segregation and integration between the epoch that goes from 0 to 9 years old, so the infancy, let's say, and between the epoch that goes from 9 to 32, so the adolescence one, and between this last one, so the adolescence one, and the early adulthood. Then it seems that these, let's say, huge changes decrease with age. So overall, what they say is that when it comes to centrality measures, so the importance of specific structures to promote the communication at the whole brain level, this is more important during adolescence. But then so the epoch going between 9 and 32 years old, but then it's less important across all the other age stages. And there's overall a pattern of increased network segregation, but there's a decline between the relationship between the segregation and age in the late life part. Overall, as I was saying at the beginning, they found that 32 years old is, they define that as the strongest topological turning point of the lifespan. So around 32 years old is where the relationship between brain structures is really changing in relation with age. Then overall, like they say that between age 32 and age 60, there are no major topological turning points, and this is mainly linked probably to the slowing of white matter maturation. Overall, there's a sparsification of the structural network in aging, and possibly related to a more weakened relationship between age and the structural brain topology. And then, I mean, they just list some limitation of this study because they, let's say, they took a lot of decisions before doing the analysis. So of course they're saying like probably the decisions that we made are changing the results that we are identifying, and also they didn't went in depth with the text differences that they overall identified. Okay, I think I'm done. It was a little bit of complex paper with a lot of information, so maybe with the questions we can go more in depth.
Yes, for sure. Thank you for presenting. Seems a very dense paper, but now that the adolescents last until 32, I feel better. So I think
Exactly.
Chris raised his hand first. So yeah, we can start with Chris.
Hey, thank you for presenting that. Yeah, it seems to be a pretty big paper. So how do they know that the measures of the changes in the configuration of the structural networks are actually biological and not from the algorithm because they are using tractography? So what if a change in the intensity that you're getting from the acquisition, depending on the age, is driving these changes? So do they acknowledge that, and or correct for that? Because how do we know that it's actually biological specialization of the network and not just an algorithmic fluke?
Yes, so they didn't actually mention it clearly. I agree with you. What I think what was the main idea was that like they try to account for this with the harmonization, meaning that they recognize that they were using different acquisitions parameters, of course. And so um, basically they just focus on this harmonization process.
Yeah, so
But
I see the combat thing. So
yeah,
combat is to harmonize between data sets.
yeah,
But still, so first you have that problem. So they are removing the influence of the data set that would in the parameters what
yes,
defined in the
exactly.
different data sets, and they are removing that influence from the results. But still, we don't know if the change because I'm a little surprised by the like how could the structural network change much over time, like especially after childhood, because like the axons we can't can we grow new axons or so I don't understand how the configuration could change at the level that we look at with diffusion imaging.
Mhm. Yeah, no, I actually agree with you. And when I was reading this paper, I was a little bit concerned because those kind of analysis have been done like extensively on the functional relationship between areas. And so it was a little bit more difficult to interpret at the structural level. So yeah, the doubts that you have, I mean, I don't have an actual answer for this, but I think there are like important doubts to be brought up to these authors. So yes,
Thanks.
thanks.
Nice. I think Lilith was next, and then we have Hervé. We have still like a bunch of minutes, so maybe we can try.
Yeah, thank you, Irene, for presenting this. I was surprised that there is like one big phase from 9 to 32, that there is almost no change. They were like all the ages were like between 9 and 32 were clumped into one phase. Because from developmental point of view, right, as far as I know, that there are big changes happening. So did they discuss this part?
Mm,
How is it, I mean, possible that it is all in one a group clumped together?
yes.
Or
So yes, they discussed this a little bit. So specifically here, um, they say so overall, like the trajectory of the topological development remains consistent. So the idea is that the relationship between topological measures, so measures of integration, segregation, and centrality, and the age stays the same, the kind of relationship. So it doesn't mean that there are no changes, but there are no changes in the directionality, meaning, I don't know, like reduced segregation is linked to the most like to the youngest individuals, okay, and this is consistent across the same age. But then what they say is that sorry for the noise. So they said like that this, I mean, they define the 9 age as the starting of puberty. So in a way, they say like this adolescent period is actually more extended and it's the same. They explained it a little bit with changes in the white matter volume and fractional anisotropy around 29 years old, changes in mean diffusivity around like 36 years old, and radial diffusivity changes, reaching the minimum at 31 years old. And then they say like there's a white matter integrity and volume increasing. So let's say that they try to give a biological explanation to this, but probably, yes, not so convincing. I don't know.
Yeah, yeah. Thank you so much. Thank you.
Thank you.
And Raphael?
My turn. Okay, thank you for presenting. Yeah, like Chris, I was surprised they looked at networks using diffusivity and yeah, the same way I would have liked to see the tensor measures like fractional anisotropy, something more simple before to go to very high dimensional field. So my question is, so when I saw the turning points, there is something I suspect is also the sampling, the density of subjects. For example, when you look at between 0 and 10, the 9, I think there is a turning point that where is the first turning point? If you go to the first.
So the first turning point is 9 years old.
Yeah, and when you see when you go up to the which is
No,
where is
sorry, you mean probably,
yeah, this one you see there is this yeah, all the turning points are where the density is decreasing. So the 9 is in the nowhere, there is no subjects here. If you go back to the not this one, the second where you can see the density, can you go?
The density was here,
Yeah,
actually.
but yeah, we don't see. Yeah, we see a little bit that.
And also
No,
maybe here, which is the frequency of.
not this one.
No.
What is the? I'm looking at it. Can you go?
Here,
No,
this
figure
one.
two. Figure two. Maybe the next one.
Yes. No, 2 is this one.
No, that is figure 4.
But maybe also here is visible.
Yeah, so the point is that when you don't have subjects, that seems to be where there is these turning points. So yeah, it's the same thing for the 36 turning point. So I'm wondering if there is not something with sampling. And it's very visible when you see the different graphs with the different measures of the networks. So you
Yeah.
have a graph 9 by 3, and you see these holes in the grill. So
Yeah, that's actually a great point. Yes, I agree with you. Yes. I don't know if you can see it here, but like here, for example, they're representing like the density and the strength
yeah,
of the connections. And yeah, it's true that around like 8 and 9 years old, there's this huge
yeah,
gap,
yeah,
which was a little bit surprising to me because when they report all the data sets that they used, they seem to have like a continuous, to have subject for all the ages. So there was not like gap in the data set. So I don't know if it was for, I don't know, some quality reasons that maybe some subject dropped out, or I don't know. But yes, I agree with you, and they didn't mention this.
yeah. And it's
Yes.
pretty important. So, for example, for the growth charts, the brain growth chart, what they use is a logarithmic, because a lot of things are happening between 0 and 20 years old, and after it's
Yeah.
more stable. And here they couldn't do that because they don't have enough subjects between them.
Yeah.
So,
Mhm.
yeah.
Yeah, thanks.
Thank you.
Okay, we're a little bit over time, but no
My
worries.
bad.
Yeah, best fault. But thank you, Irene, for presenting. Wonderful paper, very dense. Thanks for asking questions. It was very engaging. And I guess the only things left is to wish you an exciting week in science. And see you next Monday.
Thank you.
See you.
Thank you. Bye.